Hello and good day. My name is Greg Paulsen with Xometry, and today I'm going to be talking to you a little bit about additive manufacturing in the food industry. Let's just jump into things. So today we're going to be going over some of the basics of additive manufacturing, also known as 3D printing, and you're going to see I'm going to juggle those terms around synonymously with each other. I'm going to summarize some of the most popular industrial additive manufacturing processes out there. I also have some handy guides to help you choose what process and what specific material groupings may work well for your projects and their specifics. And then we're going to we are going to dive into some of the specific tips around additive manufacturing, hygienic design, and food safe production. And it's going to show some strengths that additive manufacturing has, but it's also going to show some trade-offs and how those can be conquered through design and post-processing. And ultimately, at the end, I have some great resources to share so we can continue that conversation after this presentation. A little bit about myself. My name is Greg Paulsen. I am the Director of Application Engineering at Xometry. I've been with the company since near the beginning, and before that I also had experience in running additive manufacturing labs, sourcing a heck of a lot of parts, as well as working between different technologies. So I'm well versed in machining, injection molding, sheet metal fabrication, urethane casting, and obviously multiple styles of additive manufacturing or 3D printing. Within Xometry, and for you as a potential customer, I act as a consultative role. So a lot of times I'm working in that realm of help me choose and why. So I spin the CAD with you, I'll read your technical drawings, figure out the requirements, and I can help navigate through multiple manufacturing processes and help find strengths and trade-offs of each. But today, it's about 3D printing. And I'm going to start with that big question. Why would I 3D print in the first place? And I'm going to tell you some of the strengths that additive manufacturing does have. And again, when I'm talking about this, usually in my mind, I am talking about those industrial machines. So these the machines and equipment that we run here at Xometry. Uh, First off, it is the king of rapid prototyping. When I additive manufacture parts, I can make them quickly, usually shipping within a couple of days. I have options both in polymers and metals, and I don't have a minimum. So I don't have, a setup fee or something that's associated or extra tooling. It's just direct digital printing. Because of that direct digital printing too, it's extremely low barrier to entry. In fact, the only requirement a 3D printer needs to make a part is that CAD file. That is the minimum requirement for 3D printing. So a 3D model of that design can be interpreted and sent to a printer. It's very low cost, relatively speaking, versus other tooled options. And again, we noted no specialized tooling. And this allows for some cool production freedoms, right? So if I need 12, I just order 12. If I need one, I order one. I can build in a just-in-time production. I can also do some neat things with design freedoms that 3D printing offers. When I'm 3D printing, I'm not taking a tool and cutting out from the surface of a larger block, like a billet, and creating those features. And so my access is my biggest challenge. 3D printing is generative. So I'm stacking or fusing materials, generally going from the bottom to the top, and building out my parts. So I can actually create very complex shapes that are actually easy for a printer to do, but very difficult to do in molding or machining, for instance. So it's more forgiving when it comes to design for manufacturability. And moving a little bit forward, when we think about that for hygienic designs, free of crevices or voids, smooth corners or radii, robust features, that's something that works really well with additive. And something that may not be great for hygienic design, but something you see a lot with additive is you could do some very cool lightweighting structures or topology optimized structures like lattices, which is something that's very specific to this technology. I'm well versed in over a dozen different manufacturing processes. We offer 7 unique additive manufacturing processes that auto quote at Xometry. And these are also a good gamut of the types of processes that you would see when you're looking at this industrial world. Some of this is building parts with UV photocuring resins, for example. So I have processes like polyjet or stereolithography, which are both very popular for making nice surface detail parts that are usually for our prototyping use. We have ways to fuse material together. So materials like nylon, for instance, is a really popular material for processes like selective laser sintering or HP multi-jet fusion. You could also fuse metals together. So the same process. So powder bed fusion, a laser hits and fuses basically a layer of metal at a time, building on top of each other. That's direct metal laser sintering. And then there's something that may be more common or more analogous to desktop printing that you see a lot. So that filament that gets melted out and zigzag back and forth. We call that fused deposition modeling here, and something that you could build with a lot of unique materials. So it's more of a boutique additive manufacturing process. And the last one that I have on the list here is a process called carbon digital light synthesis. That it has the strengths of stereolithography, where it has a smooth surface finish and output, but it also has the strengths of end-use polymer because it's actually printing parts in urethanes and urethane-based materials, which have much better durability and longer-term use than a strict photopolymer would. So it's kind of almost a hybrid manufacturing approach. So usually at this time, I go over a lot of different processes, and it comes down to, okay, that's a lot of choices. Is there over choice in the additive manufacturing realm? Something I like to do is build simple tools like this to help customers choose and help understand where different processes fall in the realm of things. So this is a very quick, and it's not complete, but it's fits on a slide here, a guide for additive manufacturing platform selection, and I'll go over some of the tool tips here. But again, this is all to help get you in the mindset of like, all right, I'm looking at different applications, what additive processes may work, and why. I always start with a goal. A lot of my questions are usually, what do the next 6 weeks look like for you, 6 months, 6 years look like? Because those are typically different manufacturing processes along the way. If, say, for example, I am looking for something that's quick, like a prototype, maybe I need something that has a good cosmetic look, maybe even clear. I could very quickly navigate and say, all right, let's go down here and move forward. And I could find that, hey, clear is a great option for me. And we have different options. In fact, actually, this pictured here is a Accurate Clear View SLA material with a quick clear finish, which is kind of a spray coat finish to just enhance the glossiness of that clear coat there. In other terms, I may be, a lot of times looking for functional parts. It needs to do something, right? And I could quickly look, and first off, there's plastics, there's rubbers, there's metals. For rubbers and metals, there's fewer options, so it's very easy to down select. It doesn't need to be metal, not this time, so let's bypass DMLS and Biterjet metals. Doesn't need to be rubber, not this time. Let's go to the non-rubber route. And let's say, for example, an application that I see a lot is high heat deflection. So in this route, again, very easy to take me to a couple options that have higher heat deflections. In this case, fused deposition modeling Ultim can work really well. Or through Carbon DLS, there's a material called CE or cyanide ester, which is also a very good HDT material. And you could dig deeper into the design guidance for each of those and the build sizes to figure out which works best for you. But again, a very quick down select with only a few tasks there. And lastly, we are talking about working in an environment where I need to possibly sterilize or I need to clean my surfaces, and I may want to down select just the material grouping that's specific to food manufacturing. And a lot of times that does fall into the Venn diagram of can it be sterilized? So let's take a look down here. And again, rigid plastic going through, sterilization, this could be the route to go. And there's options in multiple processes for sterilizable materials. It just narrows that list in each one of those processes there. The last thing, and again, I'm going over this very briefly because I want to get you in a mindset that there are options. 3D printing is not just one thing. It's an umbrella term of a whole gamut of manufacturing processes out there. The last thing I want to note is that each one of these platforms typically has size limitations to it. So unlike machining where I could kind of, open up the side window and take a longer part in, with additive, I'm building everything on the inside of my machine and platform. For some processes that's bigger, some processes that's smaller. Typically under 9 inches, I could do most industrial additive processes. When I go over that, you see some will drop off. Like for example, carbon digital light synthesis and direct metal sintering. There are larger platforms out there, but the commercial availability of them is lower. For a custom manufacturing job, it may be a harder barrier to entry. So I kind of drop those up there. And again, this is a guideline; it's not a direct rule. Next up, selective laser sintering, multi-jet fusion, these powder bed processes, and this is a multi-jet fusion part right here. Um, they tend to work really well in parts sub 12 to 15 inches or so, and that has a couple reasons. One is platform size. One is also that they're a high heat process when they're being built. So there also may be some thermal warpage or other nuances that happen when you go larger than those pieces there. Stereolithography, we have platforms that are about 24 to 27 inches, so we can build some larger parts there. And the largest building platform that we have is usually going to be that filament-based process, so fused deposition modeling. And we have some platforms in-house that we readily run, and we can run parts up to 36 inches in. So we have platform sizes, we have material choices through those platforms based off application. The other thing to note is that each one of these different processes, because of how they actually build the parts. It's a cured material, liquid cured material, or it's a fused powder material, or it's extruded feature. That's really going to affect the detail resolution. And this is going to come into play, especially later on in this presentation when we talk about things specifically around hygienic design and what you need to overcome with additive manufacturing. For example, this FDM piece here, you can see how coarse that is. Now, obviously that's a quarter, so object to mirror may be closer than they appear on this image, but still you get the point. One of the analogies I like to make is with pencils and pens. It's something that when I talk to customers, it's very easy to understand, and I want to share that with you as well. So when I use the laser powder bed process in additive manufacturing, I'm putting a thin layer of powder across. And then I'm using a laser to essentially etch that cross section and fuse those layers together, as well as the layer underneath, giving me that Z, that third dimension there. But I am applying heat, and that heat does have a little bit of bleed to it. So when I compare the detail resolution, I'm usually thinking something like a Sharpie fine point. So if you ever put that across a piece of paper, you know what I mean, because you see some of that ink bleed just a little bit across that paper, across those edges. So we get something finer in detail, you may see more fuzziness occur. When I look at these photopolymer processes like stereolithography, polyjet, digital light synthesis, the base material is liquid. It is actually liquid that then gets cured by light. And so my category here is Sharpie pen, because a lot of times the cured final part represents a little bit of that base material. In this case, that's what you see is that it has sharper, crisper features. It's not going to be dead crisp like a sharp right angle. Like you can see it pretty good, but if you take out a microscope, it's going to be very different than cutting a right angle with a tool. But it is probably one of the more crisp ways of doing additive manufactured parts. And then for FDM, I was actually using this redlining drafters pencil here because I thought it'd be something that is as analogous as I could get. So with FDM, you are extruding a filament. So it is like almost like drawing with a crayon, where you have a filament that's zigzagging back and forth on a layer by layer basis. That filament does have a discrete width to it, and that means that the feature sizes, very small features, the filament's trying its darndest to fill that in, but you get very different outcomes than something that has a much finer structure like a powder or liquid resin. So some paradigms to get in the mind of is I am growing these parts. When you are designing, you're thinking about growing these parts from the bottom up. I have whole webinars on how to design for 3D printing, so I won't go into that into full detail, but I wanted to note that when you start thinking about design considerations, orientation starts to become a factor as well. The other note is that printers dictate the tolerances, not the print. So based off the CAD that you generate, these digital slicing programs are interpreting the parameters of the printer, scales and offsets that it has, the CAD and the CAD that you're providing, and it's doing its best to build tool paths to create its proximity of that part. Some processes are much more accurate than others, but understand that for every additive manufacturing process that you're receiving a net shape. Sometimes that net shape's great. Plug and play, you're done. I found, when I'm researching for this industry in particular, there may be some post processes specifically because of that surface finish that you're running into. The last thing is that most additive processes, not all, but most, do require supporting structures. So we call it support structure, and it is a sacrificial structure that's generated with the part when it's growing. And it's to create a landing pad for features that don't have anything underneath it when they're being generated. A good example is, say I'm making the capital T, and I'm 3D printing that. Those arms on the capital T at the top there's a big air gap between that. And if I just put material down there, it has nothing to rest on. It'll just turn into like an umbrella shape. So you build up support structures along the side so that when you're depositing material, you have something there. And then the support structures get removed. If you have a part that requires a lot of support structures, you may see something like this. Now this is carbon DLS. It has a little bit more intense structures than others, but it's a good example. You see that little grid where there were these supporting nubs that get removed during post-processing, but they may affect tolerances and surface finish in that specific area where they were supported. So, I've mentioned this along the way, but when we talk about food safe production, and we talk about this for food and pharma, it's not just a combination of materials. Yeah, can the material be sterilized? Sure. It's a combination of that materials, that design, manufacturing method, and finishing, and the application. Like, what is going to be successful for this? Is this a clean in place product? Is it a clean out of place product? What chemicals, what other items are you using to clean? Where's it living? All this plays a role, and so food safe is an application. One thing that can help here is with additive, I can be a little bit freeform with my design, right? So I have the ability to build structures that in typical processes may have to have multiple parts to be built. And I can actually do an all-in-one assembly, maybe fill that out, create smoother features and make it easy to clean, and also reduce excess part count in critical assemblies or features, which could be very useful on the assembly floor. Good news is there is a good amount of sterilizable materials, and I have a nice little cheat sheet for you. But the bad news is that the natural surface finish of parts may not inherently meet 3A standards without some level of post-treatment. And I'm going to show you both natural finish parts and some post-treated parts. For example, here, this is actually a TPU built with HP Multi-Jet Fusion, which is that powder bed platform. So these parts, you could squeeze them and they'd be rubbery. This actually has a post finish to it. So BASF is the material manufacturer for the raw material there. But this has actually had a chemical vapor smoothing on its finish. So what does that look like beforehand? A print and ship part, so like this made out of powder bed fusion, would have this type of finish to it. So nylon 12, nylon 11s, polypropylene TPUs can be printed in a couple processes that are industrial, very regularly printed. They're very economical to be made. They're very good for bulk manufacturing. The note is that the surface finish typically is matte or sugar cube-like. So you can see here that kind of that matte surface there. So you have good feature detail, but that surface could be absorbent, very slightly. For example, SLS nylon, I can dye it different colors. The outer about 1/4 millimeter of it has some absorbent properties to it, and you can actually go in and add some pigment to that material. Even when I do a powder bed fusion process with metal, so direct metal laser sintering, I can build parts in stainless steels, aluminums, and other alloys such as titanium or nickel alloys. And when I'm building these parts, I am building from a powder base. Inherently, the surface of those parts does show up as with almost that powdery finish, as well as you get these almost micro weld like little splatter patterns. So You can kind of see around the edges here how it almost has a rough, like not really orange peely, but close to that type look to it. This is fully dense, strong steel. If I cut it in half, and same with those materials I was showing before, it looks like billet on the inside. It is, solid plastic, but the external surface of it is affected by the inherent process of additive manufacturing. When we talked about fused deposition modeling, again, I'm taking that filament and extruding it back and forth. And you can see obvious layer lines along the surface. And actually, on a rounded surface like this, you probably get the best finish possible. But if you do look at finer details around here, you can see there's some fragments, maybe a little bit of stranding happening around these features. Sometimes small detail resolution is really hard to resolve. But overall, you see that zigzagging that happens on a layer by layer basis. That being said, I have some awesome materials, polycarbonates, ABS, nylon, Ultim, and these are very popular and made very frequently. Definitely through our network, we're pumping out Ultim parts all the time. But yeah, surface finish again is the consideration here. And I mentioned before that carbon DLS is kind of that hybrid because the manufacturing process, the material itself inherently has some secondary characteristics when it gets post-cured. And this could be actually something that could almost be directly introduced into a print and go. But this is, you can see here, a smoother surface finish on this part. And again, I think this material right here, yeah, this is a rigid polyurethane material. So it's kind of a good mix of each. These little circles here, it's actually almost a play on light because of how the printing process works. It's actually really unique because if I move this around, you actually see those circles kind of appear in different places. But overall, like a smooth to the touch, solid surface for it. So this is a cheat sheet, busy slide, but it's something to look for and review as well. Different 3D printing materials, different processes have sterilizable options. I think this is good just for you to understand because usually they go hand in hand with something that can be easily cleaned or at least suffer through the gamut of frequent cleaning here. But you can see through multiple processes we have options available as well as multiple methods of sterilization. But the main contenders again are those nylons, ABS, polycarbonates, stainless steels, a lot of these urethane bases that we have here. And as I mentioned as we went along, those as-built considerations often have to do with the surface. Some of the urethanes have limited cycles based off the type of like for example doing autoclave, but overall like surface is the main consideration when I think about reusing, which is a big deal when we talk about hygienic design. So I can make parts. I can make parts in all these different materials. I can build parts that are strong. I can build parts that give me a lot more design freedom to make very unique assemblies here. How can I get them to that next level? How can I bring them to a surface roughness or a cleanability and accessibility standard to hit 3A? I think that a lot of it has to do with post-processing options. That I'm going to list out the most popular options available and some of the strengths and trade-offs. But this is something that is definitely mindful, especially as I've been researching doing this presentation here. So machining, certainly you can post-machine most rigid plastics and definitely the metals. Obviously, like when you're cutting away that outer surface, the material's like billet underneath, so I can get a machined surface out of those parts. The note there is that if I can machine the full surface of the part here, why am I additive manufacturing the part versus machining it? So that's my one consideration is sometimes I could just cut stainless steel, and again we do that all the time in CNC machining. So usually if we're doing a post machining of a part, it has some sort of internal channels or functions to that part that could not be produced in a typical manner. So understand that if you are post machining a part, sometimes that is sometimes the question is like why are we not machining it in the first place? And if it's because this part can only be made via additive manufacturing, you're still on a good route. You're still going the right direction. But we have options here. Media tumbling tends to be the lowest cost and a very quick solution. It's going to take those peaks and valleys and basically dent down those peaks, but it doesn't remove the valleys in the surface of a part. So it doesn't bring the part to a gloss, but for example, in SLS nylon, it may take something from a sugar cube and make it feel like an eggshell at the end, maybe a little bit smoother than that. It does help, but some of those inherent properties, don't necessarily change on the part itself. An upgrade and something that Xometry is actually we're adding within our additive facility, and we also have options across our manufacturing network as well, is vapor polishing. So I have an image here of a before and after of a part. This is made in HP Multi-Jet Fusion, nylon 12, but showing what a vapor polish finish is. I think this could be very attractive to this industry. Vapor polishing, what's nice is almost like anodizing, where I'm racking up parts, so I can do multiple parts at a time. It's nearly touch-free after I clean the parts off and put it through this post-processing. And it's a closed cell system that will, closed loop system that will actually chemically denature the outer surface of the part and then resolidify in a smoother state. So it's very viable, and also like this chemical vapor polishing is not just for I would say less chemical compatible options like ABS. It also is very valuable for things like PEI Ultim and nylons and things that usually aren't prone to some sort of chemical melting. So it's very exciting to have that option available. Mechanical polishing, what I mean by that is sanding. Is you can always sand up something, and it does have a high manual labor cost to it depending on what you're doing, but it is definitely an option to take a part and consider it a net shape and bring it to the smoothness, surface level that you're looking for your application. Similar to what I mentioned with chemical polishing, there's been advancements in electropolishing. So electropolishing typically only takes about a tenth, so 1/10 of a thousandth of an inch of material off of a part. So it brightens the part, but if your part's inherently rough, it doesn't smooth the part. Sometimes that means I have to do some mechanical polishing beforehand, but I also wanted to highlight some of the latest technology. So there's something called dry electropolish that is really good for metals. And in this case, this program's done through D-Light, which is the brand of this process. And it will actually help create a smoother surface and even out surface features beyond just that tenth that a normal electropolish process will do, and still retain features without routing them out. So that's something you find with media tumbling is you can media tumble the heck out of something, but oftentimes you lose your edges, you lose your corners with that. So this is a really interesting option. I'm keeping my eye on it, and I think it's very viable for this type of industry. And lastly, you could coat the part. Epoxy coatings, urethane coatings, other coatings that can smooth out, even out the surfaces, and possibly create something that's more sterile or easier to clean. That option is always available as well as a custom finish. Obviously, the cost driver to that is it's manual. You also may lose some consistency finish to finish with it. So some of these no-touch options may be more ideal if you're looking for additive production. So we went over a lot in a very short period of time. When we talk about additive manufacturing processes, we talked about some of the strengths that they could do, but we also talked about some of the challenges specifically really around surface when we're looking at this industry that we're talking about for food or pharma products. The options for that are usually in some level of post-processing to bring it through to the end. So it's a plug and play. Obviously, if you're prototyping, it's a click and go experience. And by click and go, something I want to highlight is I do work for Xometry, and we have a fantastic platform for custom sourcing parts. Whether it is this 7 types of additive manufacturing processes that I went over today, or it's machining or sheet metal or injection molding. All that all that you are able to actually quote directly through the site by uploading your 3D file. You get pricing, lead time, change your quantities, insert specifications, it updates, and you can check out. And it's a very quick experience, but allows us to do thousands of concurrent projects uh, all the time in multiple processes. And we also have the expertise in-house to actually cover all those processes as well. So it's very exciting and it's very easy to get these processes that I just described sourced out through Xometry's site. I also want to recommend, spend a lot of time making design resources, guides for different additive manufacturing processes, posts, including I actually have a great post on what makes parts food safe, which covers a lot of what we covered here today. And xometry.com/resources is a great start to find a lot of those guides. Also, check out pages like our capabilities pages or our ultimate guides to understand more in depth about each process. And obviously, the instant quoting site is also a great tool if you're trying to figure out, costs and other feedback. You can just upload your file and take a look at it there. Obligatory plug, I have to plug that we have a great referral program. So if you're exploring Xometry, you want someone else who's interested in it, you could get a unique referral code that you could share, and it gives them some money to spend on their prototyping. And if they buy, you get some money back too. It's our Give 50, Get 50 program. So check that out. And also, if you're looking to try a process, so that's one of the biggest things is when you're entering a new process into the industry, it's sometimes tough to justify, like, will this work? Will it not work? If you want to try it out, I do have a instant 50 code that you can try, and it'll help save $50 on that part. So you could get a look and feel and really understand some of that process firsthand, because sometimes that's the first step is just really get your hands on some parts and understanding like what they can do and where there may be limitations. And then feel free to contact us in our application engineering team. We're always happy to help answer any questions or guide you in a direction or finish that may work better for you. Again, I'd like to thank you for the time today. My name is Greg Paulsen. I'm always happy to talk different processes through additive manufacturing, even how they compare to other processes, like why choose machining or additive. That's something that we have some webinars on actually. If you want to contact Xometry directly, xometry.com is the place to go. Support@xometry.com or our direct line 240-252-1138 is where you can reach out, talk to some of our team, get connected with the application engineers, and just really appreciate it. Thank you so much for the opportunity. I hope I answered some questions, and if you have any questions, please feel free to reach out. Thank you so much.